I have a question to Michel Caprio
Yes.
about, you were talking about one approach, like classical old approach will be to use first to, if we take interval from 0 to, let's say, m,
Yes.
open interval, and then if we compactify this process of compactibization, then we can recreate basically arithmetics within this. Of course, this would not solve hip paradox, but how you would compare these two? Compactified open interval, which is basically isomorphic to compactified all real numbers, with your approach.
Yeah, first of all, thank you for the question. And so I guess the idea was the same. The only difference is that I wanted to achieve that without directly compactifying R. I wanted to use that function, that trick of using the function f and its inverse f minus 1, so that 0 and m like come about normally from the way I define them. And yeah, and that is interesting because then having you obtain these two bounding elements that are 0 and m, if you project a series of elements of R, so basically a series of the ones we usually study, and then it's gonna converge, right? Because if it diverges to plus infinity, it's gonna be in a one-to-one relationship with m, and if it diverges to minus infinity, it's gonna be a one-to-one relation to 0. So then the idea is that suppose you're doing some kind of analysis because you I don't know, you need to analyze a particular natural or tech phenomena, and you really would like your series to converge, but by the way the problem is structured, it doesn't, right? It's something in the form of 2 to the n, so for example. Then what you can do is you can project onto the arithmetic BM, and then you continue the analysis on that arithmetic, and hopefully you get to a nicer result, and to a result that has some that is scientifically meaningful.
Okay, thank you very much. Thanks.
Thank you.
I would like to add to the answer of Michel that the goal was to give a formal foundation for numerical computations. And we know that numerical computations cannot go for all even natural numbers. They are always bounded.
Yeah.
But those approaches that existed before, they brought inconsistent logical systems, and only non-Diophantine arithmetics give foundations that are on one hand consistent, while on the other hand they correctly represent what is going on in numerical computations. If we speak about symbolic computations, where it's possible to work with integrals on the whole, for example, number line of reals, then it's necessary to use another theory of hypernumbers. And this theory allows to make all integrals for actually all functions on a real line convergent, but convergent not in real numbers, but in hypernumbers that are very far-reaching generalization of real numbers. So this is, I repeat, the goal of the work of Michel and his co-authors was to bring force foundations, to elaborate foundations for numerical computations.
That's exactly right. Yes.
Thank you.
Okay, any other questions?
Yes.
Or
Sorry
remarks?
about. Sorry, Basti. Hi. Ciao.
Nice to see you.
Sorry about this point, because I already read on some of your paper this idea. But what is the difference with the theory of forcing of Cohen? Because effectively, also using the forcing and so using extending the cumulative hierarchy of von Neumann, you can obtain the same that you probably obtain with the hyper numbers, or not?
No, the theory of non-standard analysis is essentially different from the theory of hypernumbers and extra functions. And the difference is that the theory of non-standard analysis involves infinitely big and infinitely small numbers. However, physicists don't never encountered infinitely small numbers, even in physical theories. At the same time, they all the time come upon infinitely big numbers. Divergence is, let's say, a horror of theoretical physics, as you know. And there were different techniques of renormalization that tried to eliminate infinity. But those techniques, as actually all physicists understand, they are not grounded neither mathematically nor physically. However, the theory of hypernumbers first allows to ground renormalization techniques mathematically. I'm not speaking about physical grounding. Besides, it allows physicists to work with infinities because in the theory of hypernumbers, there are no infinitely small numbers, only infinitely big numbers. And for example, this theory allows to give a rigorous mathematical formalization of Feynman path integral. That was not actually achieved before. Also, many such formalizations were suggested. But those suggestions were different from the initial ideas of Feynman. And hypernumbers allow exactly to formalize what Feynman wrote informally about for his integrals. So there is an essential difference that there are no infinitely small hypernumbers, there are only infinitely big hypernumbers. This is the difference. And the technique of forcing is a logical technique, and actually this technique is good for the theory of transfinite numbers. And as you know, transfinite numbers, either cardinal numbers or ordinal numbers, did not allow to get interesting results in physics, and they go in a different direction from physics. They go into extension of natural numbers, of arithmetic, into infinity. A non-standard analysis was initiated by solving problems of formalization of infinitely small numbers, of infinitely small entities in mathematics. So the initial goal was also far from physical problems. And the theory of hypernumbers and extra functions was initiated by the problems in physics. And by the way, extra functions, they extend the theory of distributions. And as you know, the theory of distributions is very useful and important for physics. It's not non-standard analysis, it's not set theory, it's a physical theory of distributions. And as you know, some physicists, such as Dirac or Heaviside, used some distributions that are now called delta functions. And only theory of distributions explained and make these functions legal as mathematical structures. Before, mathematicians wrote, even some outstanding mathematicians, that such functions does not exist. What does it mean? That a function takes infinite values. For mathematicians, it was something unreal. But theory of distributions explained that these functions are simply functionals. And theory of extra functions extends. Theory of distribution is a special case, a component of the theory of extra functions. And that's why when physicists will learn how to use theory of extra function, it will extend physics, because now physicists started to understand that if infinity appears in physical theory, it has some inherent meaning for physics. Something is hinted by nature that physicists still don't understand. And so there is a mathematical theory that allows to use such structures that work mathematically rigorously with infinite entities. And actually, infinity came to mathematics when irrational numbers were brought into the mathematical horizon, into the mathematical world, because actually irrational numbers are inherently infinite. So the theory of hypernumbers go only further than real numbers.
Mm-hmm. Okay, understand. Thank you.
I think we will have to finish because it's already 4 minutes after our time of our meeting. Maybe one more question, and if anyone. Okay, because I'm sorry to push for ending of this interesting discussion, but we will have to end today's session of plenary program, and we will start tomorrow at 4 a.m. UTC, which of course this UTC will be for some of our participants, it will be morning, for some it will be evening. So thank you very much, and that's will be all for today. And See you again for UTC tomorrow.
Thank you very much.
Okay.
See you soon.
Thank you.
Okay.
Bye-bye.
Thanks.
Good evening. Bye.
And thank you to all presenters and
Thank
all
you very much.
present researchers. And I invite you to come for summit will be tomorrow session, where also very interesting presentations will be given by outstanding researchers. For example, there is present Gianfranco Basti, who will give a very interesting lecture tomorrow. Krasimir Markov will give a very interesting lecture tomorrow. Martin Schroeder will give an interesting lecture tomorrow. So come for summit will be tomorrow, for summit will be today's evening. And
Okay.
thank you once more.
Thank you. Bye-bye.
Thank you.
Thank you.
Bye.
Bye.
Thanks.
Bye-bye.